Very good. So good afternoon, everybody who's here and also who's watching online, and welcome to this week's Physics Colloquium. My name is Gordon Boehm. I'm from the University of Illinois in Urbana. I'm a co-organizer of the workshop on exploring extreme matter in the era of multi-messenger astronomy, from the quarks, cosmos to quarks, of which our speaker today, Cole, is also a participant. So it's a great pleasure to welcome Cole Miller from the University of Maryland to tell us about measuring radii of neutron stars to hundreds of meter accuracy at distances of several thousand light years, which is a phenomenal achievement here. Cole was born and raised in Michigan. He went to Caltech for graduate school, where he was Cyril Finney's first student, and where Cole characterized his time as making Cyril's latest students look better by comparison. I don't believe that. His first postdoctoral appointment was at the University of Illinois in Urbana, and that's where we first met. That was
1990.
1990, 30 years ago, my God. He worked with Fred Lamb in Urbana, and his second postdoc was actually with Fred's identical twin brother, Don Lamb, at the University of Chicago. And Cole describes it moving from Urbana to Chicago technically as the Lamb shift. Since 1999, Cole has been a professor of astronomy at the University of Maryland. He leads one of the two groups in NASA's NICER team, which infer the neutron star masses and radii from X-ray data. The results are described today. I want to mention that a flyer was sent out that mentioned the wrong public speaker for the public talks later today. There will be a public talk online only at 5:30, and it'll be Greg Stevens. Is Greg here? Okay, he's in town. He'll talk on patterns in posture, chaotic worms, and other surprises from the physics of animal behavior. And I also want to remind you that right after the colloquium, there will be reception down at the other end of this corridor, just immediately outside the Smart Hall with wine and cheese. So look forward to continuing the colloquium conversations there. So Cole, please.
Thank you very much, Gordon. It is a tremendous pleasure to be here once more. I've always enjoyed Aspen, and it is therefore entirely appropriate that this is going to be the first in-person talk that I have given for a very long time. May there be many more. I am indeed going to talk about measuring the radii of neutron stars. This is, of course, a broad set of physicists who attend the Aspen Center for Physics, and so I'm going to try to give you some context. What are neutron stars? Why should they be interesting to lots of physicists, not just the specialists? What would we get if we were able to measure a precise radius? How we measure radii, and of course, the usual future prospects. Now, because again, this is a colloquium, it's important to be able to appeal to a broad variety of physicists, but also to give some challenge to the specialists. And as far as my philosophy on this, I will mention that many years ago, I was fortunate enough to get on the short list for an assistant professorship at a university. And I knew this was very important. I really had to do a great job for my talk. So I worked really hard to make my entire talk fully understandable. I eliminated all but the most essential equations. But I was told later that many of the professors at this university felt this disqualified me for the position. Because you see, I'm a theorist. And for a theorist needs to at least be partially not understandable, and they have to have complicated equations. Now, I don't want to repeat that error on my part, and therefore, here are some equations. Okay, now, my hope is that my demonstrated ability to latex these equations has convinced you that I am, in fact, a serious theorist, and therefore I can go back to being understandable. Okay, so let's talk about neutron stars now. Where do you get neutron stars? And the simple answer is you get a neutron star when a big star falls down and goes boom. So in particular, we have a variety of possible endpoints of stellar evolution. If you have low mass stars, these are stars beginning their lives less than 8 times the mass of the sun, these have a comparatively gentle end. They puff up, they shrink down, and they leave a white dwarf, which is something of stellar mass, but approximately the size of the Earth. For more massive stars, they have much more spectacular ends. These undergo a core collapse supernova, where they go through a sequence of nuclear fusion processes until at the end, they are no longer generating energy by fusion. They can't hold themselves up. They build up to a certain critical mass and collapse. These can leave neutron stars or black holes. Now, everyone knows black holes. In fact, I have, of course, in the before times when I was flying regularly, if I had a seatmate who learned I was an astronomer and I wanted to talk to them, I would tell them that I study black holes. If I didn't, I would tell them I study neutron stars. I've even had friends tell me that really a neutron star is a failed black hole. However, I want to try to convince you that neutron stars are very worthy of study from a broad variety of physics perspectives. In particular, and this is a wonderful figure that was produced by Donny Page of UNAM in Mexico City. If you look at the physical extremes of neutron stars, they have the strongest magnetic fields in the natural universe, the second strongest gravitational fields next to black holes themselves. They have superconducting superfluids in their centers with transition temperatures of at least 10 to the 8 Kelvin. They have remarkable aspects of condensed matter. In fact, if you think about the frontiers of physics that are probed in different aspects of neutron stars, these include particle physics, nuclear physics, condensed matter physics, plasma physics, hydrodynamics, QED, general relativity. As a result, by studying them, we really have the prospect of extending our fundamental knowledge of physics as well as the associated astrophysics. The main focus here is going to be on that giant question mark in the center. What is it that is going on at the center of a neutron star? As I will explain, this is a state of matter that cannot be probed directly in laboratories, and therefore we have real prospects of extending especially our understanding of nuclear physics. But what do we have? Mainly nucleons, hyperons, quark matter, who knows what. So to try to get at this, we're going to talk a little bit about neutron stars. We're going to be going in greater and greater depth. But in addition to doing that, I want to actually use one of those essential equations. You can learn a great deal about neutron stars. You can really encapsulate much of their physics in this sense. If you think about just the old uncertainty principle, delta X, delta P greater than or equal to H bar over 2. Now, one thing that this implies, which you can perhaps convince yourself of if you recall quantum square well experiments, just the old one-dimensional ones, that if you have a certain separation between fermions, this gives you a minimum momentum, the Fermi momentum, which, as you can see, is squiggle h bar n, where n is the number density to the 1/3. The squiggle, of course, is indispensable for astrophysicists. Maybe you're twitching and wondering about the 3 pi squared to the 1/3 and such. But for an astrophysicist, it is sometimes said they look at dy dx and cancel out the d's to make some progress. I would actually say that what we try to do is distill things to the simplest possible component, which still gives us some insight. So in this particular case, this quantum mechanical Fermi momentum is something that can act in other ways as an actual momentum. And in particular, there is an associated energy, the Fermi energy, which for non-relativistic momentum, so much less than mc, where m is the mass of the particle, contributes to the energy, which is pf squared over 2m. And then the ultra-relativistic limit, it's p times c, as you would expect. An important aspect of this is that if you have a system that has similar number densities of electrons, protons, and neutrons, then because the electrons have such tiny masses compared to the protons or neutrons, and that divided by 2m there, it means that at the similar number densities, the Fermi energy of an electron is much larger than the Fermi energy of a proton or a neutron. This is important because if you think about the balance which is struck between protons, electrons, and neutrons, if it becomes expensive enough to have electrons, they can combine with protons to produce neutrons and, of course, neutrinos. That is to say, when the Fermi energy of the electron plus its rest mass energy is greater than the difference in rest mass energies between a neutron and a proton, you start favoring having more neutrons. So this is why these are neutron stars. The first thing that happens is that you end up with more and more neutron-rich nuclei. But when you get to a density of about 4 times 10 to the 11 grams per cubic centimeter, it starts becoming possible to have neutrons exist in a free fluid state outside of nuclei. This is called neutron drip. We are still nowhere close to nuclear density, which is about 500 times larger than that. But as we progress to even higher densities, then we get some interesting surprises. One of which is the topology of nuclei. So you start bringing these together in ways that are called pasta. So the idea here is that a study which was done, very nice study in 1983, Ravenhall, Pethick, and Wilson. And by the way, I was very sad to hear earlier today that about a week ago, Jeff Ravenhall died. He's somebody I liked very much when I was at the University of Illinois, very kind to a junior person such as myself, and a great contributor to nuclear physics. This is one of his signature contributions. If you think about the competition, as it were, between bulk energy and surface energy, you find that under many circumstances, probably including those in neutron stars, that as you get to higher and higher density, then you go from a state where you have mainly your nuclei agglomerated in balls or spheres that to some people might look like meatballs and others like maybe gnocchi. But then as you go to higher densities yet, these come together in rod-like structures, indeed spaghetti. Yet higher densities, those rods merge to form plates, lasagna in fact. And then as you get to higher and higher densities, you have the inverse. So whereas previously you had high density nuclei in a relatively low density sea of free neutrons and electrons, then it inverts. So you get to anti-lasagna, anti-spaghetti, and then holes like Swiss cheese. So this is the pasta antipasta sequence. So this is some of the fun and enjoyment that you can get when you think about neutron stars. If we go even deeper, now we are in a state where we are at nuclear density, which is maybe 2.7 times 10 to the 14 grams per cubic centimeter, or we are at higher densities. So at least at this outer core, there is a relatively smooth fluid of neutrons, protons, electrons, and muons. The muons are there because the electron Fermi energy is so high that if you forced there to be only electrons, you would not be at the energetically lowest state. So you actually introduce the more massive cousins of electrons, the muons. Here you have superfluid neutrons and superconducting protons, as long as the neutron star is old enough, maybe even just thousands of years or even less, that the core temperature is below the transition temperature. So when I talk to some of my friends at Maryland who work on superconductors or superfluids, I laugh at their idea of high temperature. You know, hey, we got to 250 or 300 and some Kelvin with high pressure. Yeah, that's great. Tell me when you've got a few orders of magnitude higher, then we'll talk. It is not known how far down this is the dominant composition. And this leads to the main part of this talk, the real focus, and indeed one of the prime focuses of this workshop, which Gordon is one of the prime organizers of. That is what happens at even higher densities, at a few times nuclear saturation density. This is the great unknown. You can make arguments in the same way that with the extremely high Fermi energy of electrons, you're going to drive toward more of a neutron-rich composition, that at high enough densities, the Fermi energy of neutrons is sufficient. You would expect new particles to appear as stable particles because it's energetically favorable. But there are a lot of uncertainties about the mutual interactions, meaning that there is no agreement about what this is. It could be still mainly neutrons and protons for much of the bulk of the star, mainly hyperons, which are 3 quark bags involving at least one strange quark, free quarks, self-bound strange matter, a minority opinion, but possible, mixture of phases. And there's a strong divergence of these theories. This happens in any community, of course. There are fierce arguments about details that are somewhat distant from those outside the community, but it does mean that there are some interesting possibilities of contributing to our understanding of nuclear physics. So this is a special state of matter. And the reason why nuclear physicists are so interested in the study of neutron stars is that the state of matter in the cores of neutron stars cannot be reached in laboratories. It's several times nuclear density. It's very neutron rich, unlike nuclei. It is also very cool. Of course, in astronomy, anytime you use something like hot, cold, big, small, you have to say with respect to what. So in this case, we're talking about the thermal energy is much less than the Fermi energy, which means that a temperature of 10 to the 9 degrees in the core of a neutron star is cold, although it's higher than I personally prefer. So we cannot access this state in laboratories, and this means that by study of neutron stars, we have the capacity to extend our understanding of nuclear physics. How then can neutron star observations help? Well, before getting into that, I feel my conscience prickling me a little bit in the sense that I need to confess something. We sell this to you by the excitement of composition. Is it hyperons? Is it free quarks? All these amazing things. But the thing is that when we do neutron star observations, what really matters in terms of the observables, the mass, radius, tidal deformability, etc., is the equation of state, the pressure as a function of energy density. And the reason it's only the function of energy density is that it's cold and we assume it is in equilibrium. So we do not have compositional differences. We do not have an extra dimension of temperature as we would in the full QCD phase diagram. It is possible in the future that if we're able to observe cooling of neutron stars with very precise and reliable measurements of the temperature as a function of the age and mass of the neutron star, maybe we could access this. It's not there yet, and even those don't point uniquely to a composition. So that's what we're doing. And essentially, if we can do our measurements well enough, then we can throw them into the octagon where the nuclear physicists can fight about whose composition is best. The measurements that have been made that now pertain to the equation of state of neutron stars involve masses, tidal deformabilities, essentially meaning if you expose a neutron star to a gravitational tidal field, how much does it distort away from the equilibrium spherical configuration, and radii. So now let's explore these in turn. First, neutron star masses. So I don't want to keep saying equation of state, so we'll just say EOS. Again, pressure is a function of energy density. If you have a specified EOS, this means that you can predict the mass and radius and a lot of other things. And here, by the way, I am going to be specializing to neutron stars that aren't rotating too fast. And I say this in the sense that too fast would mean a neutron star spinning so fast that matter at its equator is almost flying off. But that's a frequency which is at least twice the highest frequency ever seen for a neutron star and is a few times larger than what you see in the stars that we care about. And this turns out, therefore, to be a very minor concession to simplicity. As I said, we're assuming this matter is in an equilibrium. This is a statement likely to be true, but just to give you an idea of why we can't guarantee this, I am not in equilibrium. I don't mean by that psychologically. I mean, from a nuclear standpoint, I am not in equilibrium. Otherwise, I would be nickel 62, and I don't think I am. And that's because the energetic barrier between me and the nuclear equilibrium is enormous compared to the energy that I can bring to bear, like my thermal energy. But in the cores of neutron stars, it is believed that the energetic barriers are small enough that we should get to the equilibrium state. As a result, and this is often a bit of a confusion, it is believed that at least at these high densities, above nuclear saturation density, there is a unique equation of state for neutron stars. That is not to say that all neutron stars have at their core the same type of matter, because masses and central densities can differ. It's just that there is believed to be a unique P of epsilon for neutron stars. Among other things, you also can predict the maximum mass that you're going to get for a neutron star. Here on the right, what I'm showing is a plot from a paper of about a decade ago, which shows the mass for the specialist. This is gravitational mass, the radius, the circumferential radius, for a variety of candidate equations of state. So we see that for a given mass, each of these has a prediction for the radius, but also that there is a curling over at a maximum allowed mass. Among other things, if your equation of state is to be viable, it must accommodate the largest measured mass of a neutron star. If it cannot do that, it is a dead equation of state. And being able to accommodate that doesn't mean your equation of state is right, of course, so it's a one-way thing. So as a result, our first question is, what masses have been measured? The most precise measurements of neutron star masses, and indeed the most precisely measured masses of anything outside the solar system, come when you have a system of a binary with two neutron stars, at least one of which appears to us as a pulsar. Pulsars, you may know, are the most precise and reliable natural clocks in the universe. And therefore, it has been possible to measure not just the standard parameters of a binary, such as the orbital period and the line of sight speed, but many so-called post-Keplerian parameters that give you not only precise masses, but also checks on the underlying theory of general relativity. This is why, very deservedly, the 1993 Nobel Prize in Physics was awarded to Russell Hulse and Joseph Taylor for their tests of general relativity by looking at binary neutron stars. Very good. So now we're looking at these stars, and some of them are very precise, some of them not so much, but hey, they cluster. 1.35 plus or minus 0.1 solar masses, outstanding. So looking at this, it's clear that there is a low maximum mass for neutron stars, perhaps 1.5 solar masses. Indeed, that very argument was made repeatedly up until 10, 15 years ago by different people. However, it is essential to remember in anything involving astronomy that we are profoundly subject to selection effects. To use a deep philosophy that would be appropriate for Yogi Berra, we can only see what we can see. And the thing is that we can't see everything. So just as an example, if we look at this set of neutron stars, or indeed all the neutron stars for which we have even a hint of the possibility of a mass, it is several tens of neutron stars. There are probably several hundred million neutron stars in our galaxy alone. So we're seeing a tiny fraction. So we have to be aware that it could be that maybe this doesn't indicate some limit based on the equation of state. Perhaps this is just telling us that this type of system has to go through a narrow keyhole in order to become a double neutron star system. And in fact, now we know of 3 neutron stars with masses at around 2 solar masses. So this is the sequence. So there's been a substantial discovery. The current record holder in terms of the best estimated mass was discovered by Thankful Cromarty and colleagues, about 2.1 times the mass of the sun. So that very narrow range for the double neutron star masses is a red herring when it comes to thinking about the actual maximum mass. What this tells us is that neutron stars can get up to 2 solar masses or more. And this turns out to mean, in terms of the equation of state, that the EOSs that are too soft, meaning that they have pressures too low at the relevant densities, are eliminated because they cannot reach this type of mass. That's already a major improvement in our understanding based on the measurements in astronomy. The next big thing is something which, well, I hope you've paid attention to over the last few years. Less than 6 years ago, there was the first direct detection of gravitational waves. This was a double black hole system. But neutron stars have information which they can deliver to us through gravitational waves that has tremendous potential and actuality. On August 17 of 2017, there was in fact a double neutron star coalescence, which was observed with the LIGO and Virgo ground-based gravitational wave detectors. So I'll mention a little bit more about that one in the next slide. But first, I want to give you a broader perspective. Gravitational waves come from mass motions. For these to give you anything detectable, it has to be a whole lot of mass moving really fast. So this gives you some information about the bulk of the neutron star. Right now, the best information we have from gravitational waves is about cold matter in the cold sense that I was discussing earlier. So these are neutron stars that are sufficiently far separated from each other that they still have temperatures much less than their Fermi energies. But there are also prospects in the future, depending on whether we are lucky or good, which can tell us about the hot equation of state. The lucky part would come from the supernova in our galaxy. If there's a supernova in our galaxy, we may be able to detect gravitational waves from the core collapse. It's a very subtle thing because spherical motion generates zero gravitational waves. There's only deviations from that that can give you gravitational waves. The best estimates are that it would need to be in our galaxy to be seen. But if you do see that, you get to see the initial proto-neutron star and the settling down from temperatures of 100 MeV. Another way that you could get at hot equations of state comes from neutron star mergers, where they come together, and again, we're talking about 50 MeV or more, and differential rotation, magnetic fields, lots of good stuff. That, however, is where we're going to have to be good. Supernovae, we need to be alive at the time, right? Once every 100 years. So, yeah. But we can be good, and people are trying to be good in a moral sense by constructing ever more sensitive gravitational wave detectors. If you have the next generation of ground-based detectors, mid-2030s perhaps, this is something that may be able to get the necessary sensitivity for realistic distances to be able to get up to the high frequencies of those mergers. Right now, we need to be quite lucky. It needs to be really, really close. So various quantities matter for different gravitational wave observations, but all of these are fundamentally based on the EOS. And so this gives us checks. Are we getting a consistent story? The story that we now have comes from this event, this GW170817 from 4 years ago. And the idea here is if you have two objects, stars or whatever, that are very far apart from each other, then from the standpoint of their orbit and their gravitational waves, they behave as if they were point masses. But bring them close enough together, if they are neutron stars instead of black holes, they exert mutual tidal gravitational fields on each other. And as a result, they distort from the equilibrium spherical configuration. That distortion takes energy. The source of energy is the orbit. So as a result, compared with what you would have from, say, two black holes of the same mass as your neutron stars, you spiral in a little bit faster. So you can actually see the phase of the gravitational waves evolve in a way that would not be consistent with point masses or black holes. This is something which is, we're hoping for more and more sensitive detectors or closer events. Right now, we have tentative information, maybe of some tidal deformability, which is what this is called, how much you can go away from a sphere. But right now, it certainly produces at least an upper limit on that. So whereas the existence of high mass neutron stars eliminates the softest equations of state, the upper limit on the tidal deformability places a limit on the hardest equations of state. So these are playing well together with each other. But what about radii directly? You can kind of get some info of this from tidal deformability, but throughout the years when I've talked to a number of nuclear physicists and I've asked them, hey, suppose you could get one piece of information measured precisely and reliably about a neutron star, what would you choose? More often than not, it's the radius. We can kind of see why that is. Again, as I'm showing the same diagram as before on the right, because here we have a whole bunch of these mass radius curves. And let's say we're asking only about the ones that meet this maximum mass threshold. You can still see that, at least from this set of possible equations of state, there's a wide range of possibilities. So if you knew the radius, you'd really be able to get down there. But there's a problem. When you think about masses, the measurement of masses kind of comes down to the fact that gravity is a long-range force. Look at a binary, you see stuff being whipped around by gravity, you can kind of figure out the mass. Okay, it's a little more involved than that, but that's basically it. Radius has no effect on a distance like this. So you need to be able to use other techniques. Now, some of them you might think you could use just fine. As an example, ordinary stars, like the sun. How do you figure out how big they are? Well, okay, I mean, some cases like the actual sun, you can get an angular diameter and you know the distance and you get the size, very simple. But most stars are points from the standpoint of our observations. So you need to do something else. Not a problem. You're clever. All you have to do is you notice that the spectrum is a lot like a black body. And you can measure the distance by parallax. You can get the flux. You can measure the spectrum. It's a black body kind of. You put all the stuff together, you get the radius. You check against the radius of the sun or Betelgeuse, which you can also angularly resolve, or astroseismology, and it all works. So you're in great shape. Filled with confidence, you do the same thing now with neutron stars. You notice that in the X-rays, their spectra are pretty close to black body. In fact, it's a statistically good fit. You're in great shape. You do the same procedure and you get answers 2 to 5 kilometers. No. So there are some problems here. The problem is that you can get a statistically good fit, but be very far off. One of the big challenges for neutron stars is that unlike ordinary stars, which have a lot of spectral lines, very narrowly defined, basically from bound atomic transitions, which can give you tremendous amount of extra checks on your information. Neutron star atmospheres are fully ionized. There are no lines, there are no edges that come from surface atomic features. Because this is so broad, it's very easy to fit. So you can get excellent statistical fits to things and be wrong, even if you're not using just black body curves, even if you try to use more sophisticated methods. Now, there's some things you can do, and I want to point out in particular, Jonas Natala has led some work from a few years ago, trying to put in little extra degrees of freedom, like not requiring that the entire surface have the same temperature. I think this does a better job, but there's worry about systematic error. This is where NASA's NICER mission, that stands for Neutron Star Interior Composition Explorer, it's NASA. This is where you can get extra information, and this modeling can help. A lot of work that I have done with Fred Lamb and our colleagues suggests that the extra dimension of data that is brought in by NICER is that you not only have the spectrum and flux, but you also have rotational phase information. NICER's timing is astonishingly good. It can time the arrival of individual X-ray photons to better than 100 nanoseconds. So much so that it is possible to obtain spectra which are rotational phase dependent. This extra dimension of data gives us something which, as far as we can tell, means that we're not going to be fooled in this very problematic way. In particular, we have done a lot of synthetic data analysis where we know the answer, and so we can check what we're getting from our analysis. And we can do things like we have a standard set of assumptions that we use when we fit, and then we compare them with synthetic data we've generated using other assumptions. Maybe we analyze with different spot shapes than we generated, or with different spectra, or with temperature gradients and anything. But here's the key thing. Unlike the situation, which is common when we use just the flux and the spectrum, where you could have an excellent fit but be very wrong, significantly biased, that does not appear to be the case here. From what we've analyzed, if we get a good fit, there's no significant bias. Now, obviously, we're continuing to push this, but this is what has encouraged us to do the analysis of the NICER data with the belief that not only can we obtain precise answers, but we can also get reliable answers, which is very important. The basic idea of NICER, and obviously I have lots of backup slides if you want to see them, is that you have a neutron star not accreting matter actively, but has hotter regions or hot spots on it that rotate with the star. And this is going to produce, therefore, a rotational phase-dependent spectrum as the spots come in and out of view. And this has a lot of different parameters to it, like the shape of the spots, the location, the temperature, the size, how many spots there are, and so on. And you then basically do your Bayesian thing of forward folding. You take a given combination of mass, radius, inclination angle, blah, 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 and you fold it through the detector response. Then you compare with the data. And you do it 100 million times, and then you ask, what is our answer in terms of mass, radius, and uncertainties? So what I'm now going to do is I'm going to present work from our team's analysis of nicer data, and in one case, also data from the European Space Agency mission XMM-Newton on 2 different pulsars. But as Gordon mentioned, there are 2 teams, and the other team, I also very much encourage you to look at their work. This is a team led out of Amsterdam, but I'm going to focus entirely on our work. The main results here, I'll just put these up, but of course you can look at the papers for far more detail. We are looking at 2 neutron stars, both of which are spinning fairly rapidly, one at about 200 hertz, one at about 350 hertz, which incidentally means you're talking about objects the size of a city, which are spinning around about as fast as a kitchen blender. So in the first case, we have an isolated pulsar, no stellar companion. This means we do not have the possibility of getting an independent mass estimate or an independent estimate of our inclination angle to the orbital axis, which are useful in our analyses. But we get a radius of about 13 plus or minus 1 kilometers and a mass of around 1.4 solar masses. For the more recent one, which we reported earlier this year, this is the heaviest precisely measured neutron star. There we do have a companion, and that's lucky because in X-rays, this one is about 20 times fainter than the first one. So we really need every other bit of information we can obtain. And the radius we find at plus minus 1 sigma ranges from about 12 to 16 kilometers. Now, for those of you who are really into this sort of thing and looking at those radii and are thinking, oh my God, 16 kilometers is really enormous. That's ruled out. Our philosophy here is that when we're doing our analysis of the nicer XMM, radio, et cetera data, we allow the radius to be anything that fits the data. However, later, when we are trying to determine the implications for the equation of state, at that point, we apply other considerations. For example, considerations for the equation of state, like the nuclear priors or tidal deformability, or so on. So that's why we can go up to such a high radius in this case. So here's a mass radius diagram for the first of the pulsars. And so here we have mass and radius, and we have a bit of a correlation between them. And these are details I can explain more if you like. We've actually tried different models, in one case having 2 spots and one having 3 hot spots, and they give very consistent results. So that's fine. But the thing to emphasize here, remember I said that work by Fred Lamb and myself and our collaborators has indicated that if you get a statistically good fit, then the answers seem to be reliable. But that means we have to check whether we have a statistically good fit. What we have here in this old TV test pattern is on the vertical axis, you can think of this as increasing energy. So this is energy channel within the detector. And on the horizontal axis, we have the rotational phase bin. So we divide this already very small rotational period into 32 bins. The gray scale indicates chi. Chi is the signed square root of chi square. And the thing you are looking at here is no patterns. If there were obvious visual patterns, that would be a sign of a potential problem, because maybe there would be some systematic issue, but there is not that. We can also do, for example, a standard chi-square per degree of freedom test, and it works fine. But I do want to re-emphasize that the chi-square or any other goodness of fit test is a one-way test only. If we get a terrible fit, something is missing in our model or wrong with our model. If we get a good fit, at least it passed that test, but we can't necessarily get drunk and assume we were right. The heavy pulsar, this J0740, this is named by astronomical convention. That's the right ascension, which is kind of like the longitude. Here, we really need to bring in a lot of extra information, from radio observations to also the XMM X-ray satellite. And what we have here is a corner plot. This is what we get for the radius after we've analyzed everything. This is the mass, the gray histograms after we've analyzed everything. The dashed line is before we analyze the X-ray data. You see they're not very different, and that tells you how important it is that we use the radio information. So this is the result I had quoted earlier. And indeed, when we do the same sort of comparison as before, once more we find that this is a statistically good fit. Chi-square per degree of freedom is fine. Our test pattern, which is now in color because that's how TV evolved, there's no obvious pattern, and it also fits the XMM data well. In any case, the point is there's no indication of a problem here in the fit. So this means that we take a deep breath and move forward with some of the implications that we would have. Here is where I'm going to be speaking a little bit more to the nuclear specialists, but the point here is as follows. We want to see how our constraints on the equation of state evolve as we add in more and more measurements and constraints. And I'm showing not just the sequence of constraints, but also because we don't know the right form of the equation of state above 1, possibly 2 times nuclear saturation density, there are different ways to extrapolate to high density. So these are different frameworks for the equation of state. So take a little time to go through this. The different frameworks, the one on the top left is a piecewise polytrope. So a polytrope is the pressure is proportional to the density to some power, where you match these at certain joining densities. This is a popular way of extending the high densities. The so-called spectral equation of state, I won't describe in detail, except to say that this is the favorite of the LIGO and Virgo gravitational wave communities. This GP is something called the Gaussian process approach, which has been introduced by Phil Landry and Reed Essick, and it has a lot of advantages. There are many other possibilities. These are the 3 that we chose because we want to know whether our final answer depends a lot on what we started with. For each one of these panels, the dotted line, the lower bit is the 5th percentile of the pressure at a given density, and the upper is the 95th percentile. That's true for all these line types. This is the prior. This is before we add in any information. It's just our initial state. Then adding the next bit is the information we had prior to NICER. This includes high masses, tidal deformabilities, among other things. The dashed line, the next one up, is when we add that first pulsar, the solitary one, and then finally the solid line are with all included, including the recent heavy neutron star. And then in the bottom right is the final for all of them. You can see there's some still dependence on which framework we are using, but compared with the initial gigantic spread, this is really pretty tight. I would say that based on all of this, there's fairly good convergence between about 1.5 and 5 times nuclear saturation density, which is a wonderful thing. It means that we are beyond the stage where priors dominate. We are in a data-driven era. Another way to think about this is mass radius constraints. You recall that given a particular equation of state, we can predict the radius as a function of mass. So we can do this again, starting with our prior and then adding pre-NICER, the first NICER pulsar, and then finally the second one. Here we are focusing on the Gaussian processes framework, but it's similar for all. In the pink band, we see the middle 90% of the radius as a function of mass. In the blue band, it's the middle 50%, but just by eye, you can see that clearly adding information helps a lot. And in particular, comparing the pre-NICER with what we have after including both NICER pulsars, there's a dramatic improvement. Indeed, even among all 3 equation state frameworks combined, what we find is that at a standard neutron star mass of 1.4 solar masses, the plus minus 1 sigma range is 11.8 to 13.1 kilometers. plus or minus 5%. This is pretty impressive. But just for fun, I want to put this on more of a human scale. This is one of the advantages of working with NASA. When they have a press conference, they allow you to work with graphic artists who know what they're doing. So we're going to do the same progression here, just for a 1.4 solar mass neutron star, but against a satellite map of Washington, D.C. So you can see the little red band is the Capital Beltway, should be its name. And we have the inner circle being the -1 sigma for a 1.4 solar mass neutron star, and the outer is a +1 sigma. Again, we're going to start with the prior, which is called here theoretical, and then add information. So here's this relatively broad range for the so-called theoretical. And now if we add information pre-NICER, we can see that this is significantly contracted, but you add the first and then finally the second of the NICER pulsars, and now is where you're getting this remarkable precision. So as Gordon said, we have a remarkable deal, really a testament to the hard work done by everybody in all these communities, radio, X-ray, gravitational wave, the nuclear physics community, that we are able to measure to a precision of the size of a college campus, something the size of a city at a distance of thousands of light years. Just a second. So to conclude, and then I'll be very happy to have lots of different questions. I would say that right now for densities up to roughly 5 times nuclear saturation density, we are primarily driven by data rather than by prior assumptions. And the prospects are bright for future improvements. NICER itself will report on other pulsars. There's another one that I hope we're going to be able to report on later this calendar year that should add good improvements. And in addition to that, if NICER is funded for an additional few years by NASA, we will significantly improve our data store and our understanding of the instrument, therefore improving even our previous measurements. In coming years, we of course hope for additional and more precise measurements through gravitational waves of tidal deformabilities. There is some possibility, which has been discussed for more than 15 years, that there's even one pulsar where we may be able to independently measure the moment of inertia, and we already know its mass to better than a part in 1,000. Overall, it's a remarkable thing. Just in the past decade, we've gone from having very little astronomical information about the equation of state of high density matter to a data-rich era. It is truly a good time to work on dense matter. Thank you.
Thank you very much, Cole. That was lovely. Call for questions.
Thank you very much. I just wonder if you can elaborate a bit more about that fire that suppressed those higher radius and how that will affect the influence of your results.
The prior that suppresses higher radii. Yes. So for us, of course, we do not suppress that at all. If you think about, perhaps you're thinking about the other team's work, which has where they actually impose an upper limit of 16 kilometers on the radius.
Could you repeat the question, please?
Sure. So the question was, how much does it affect the inferred equation of state if instead of, say, in our analyses, allowing the radius to be whatever is necessary to fit the data, we impose a constraint, say an upper limit of 16 kilometers or so. And the answer is that for the first of the NICER pulsars, it's not even relevant. The X-ray data are sufficient that those radii are excluded just by the data. For the heavier pulsar, it does make a bit of a difference. And in fact, something that I think I can show here, because this is, let's see, say the difference, yeah. So when you look at the results which were reported by the 2 different groups, analyze the heavy neutron star from NICER, the, say, -1 sigma radius looks very significantly different. One of the reasons is that they do impose an upper limit of 16 kilometers. The main thing turns out to be the assumptions about how the 2 X-ray instruments are calibrated with respect to each other. When you use something which is based on the measurement, so this is something that's a fairly tight value, that's what we get. They're using a much broader prior on that. So these are some of the differences that come in. But in terms of the implications for the equation of state, they're relatively minor because you have a lot of other components of the data that are coming into it.
Is it not play a big role, or is it an introduced by system magic?
Right, it plays a role, especially because at high masses, that's special leverage that you get, but it's not something that is decisive at this stage.
Could you again repeat the question?
So this is just trying to make sure you're understanding my answer. So is repeating my answer.
Meg?
I'm gonna take my mask off. I don't think you'll hear me, but I'm Cole. Thank you for a really nice talk. Can you say what the radio data are telling you, and also why chime? Why is that the instrument of choice for the radio?
Okay, and I think I'll repeat questions from this audience so that people in Zoom can hear about that. So the question is, for the heavy pulsar J0740, what is the role of the radio observations, and why in particular is chime, which is the Canadian high intensity mapping? Sure, thank you. So there, the thing is that this pulsar is a system where you have a pulsar and you have a companion, and it's a nearly edge-on system to us. This means that from the radio pulses from the pulsar, it is possible to get a fairly good measurement of what is called Shapiro delay. So Shapiro delay is what you get where you have, if for example, the companion is on the far side of the pulsar from us, then more or less the radio waves come directly to us. If it's between us, then the radio waves have to go around, take a longer time in order to get to us. This delay is very important in getting mass measurements. So not only do we get the very good mass measurements, we also get the observer inclination to the orbital axis. For our analysis, what we need is the observer inclination to the rotation axis. There's a little bit of slack there, but the assumption is that the evolution of these systems has very closely aligned the rotation and the orbital axis for these systems, because the assumption is there has been a spin up of the pulsar by accretion from the companion in times past. Chime plays a critical role here, in addition to observations by the Nancy Observatory and Green Bank. But chime has the advantage that it sweeps past the same part of the sky over and over again. And it turns out that for Shapiro delay, the most important observations are the ones very close to where the companion is between us and the pulsar. So it's that continued addition that'll help, also meaning that as the years progress, the precision of those measurements is going to improve.
Nico?
So, when you go back to the mass radius of stereo, they seem to be essentially ruling out first order phase transitions, say nuclear saturation. So, should I interpret it that way?
No, and I'm glad you mentioned that. So this,
Repeat the question.
okay, sorry, yeah, the question is, given what we're showing here, these mass radius things, that this might seem to rule out first order phase transitions. The thing is that what I'm showing here is an envelope. We are not showing each individual mass radius curve. So for example, one thing that you could look at here is it appears that we're always going up and to the right somehow. As you go to higher masses, you're going to higher radii. What's really going on is that only the equations of state that allow there to be high mass can factor in here, and those also have higher radii. So there are, in fact, viable equations of state which come in and have a drop in radius and then go up. So this is an envelope. This is not representative of individual equation of state, mass radius curves.
Let me just say, what is a viable equation of state?
So a viable equation of state in this
As
sense,
opposed to an equation of state.
right. So you can phrase this in a statistical way. You can say, here's an equation of state. So here's a candidate pressure as a function of energy density. Now that one is going to predict a certain maximum mass, a radius versus mass, a tidal deformability, and so on. So we can take these and compare them to the data, and we have a set that in a statistical sense do well in comparison with the data. So it's a fuzzy thing, but that's what I mean by a viable equation of state.
Can you have a secondary branch outside of those contours or not?
Yes, so this, remember, is the question is, can we have a secondary branch outside the contours? The answer is yes, you can. Remember, for one thing, this, say the pink is the 5th to the 95th percentile, so it's certainly possible to have something outside that. And second, it is possible, although not so easy once we get to our full precision, to have something that goes up, drops down, and has a second peak.
But it has to be inside of it.
No, because that's the 5th to 95th percentile.
So I assume that the sound speed of these objects is basically C, right? So,
Oh, no. In fact, there's a huge, sorry, I keep having to remember to repeat. The question is the sound speed in these objects nearly C? And there is a sub-community that argues fiercely about this. It turns out that these measurements do not strongly constrain the sound speed. Essentially, by the sound speed is like the sound speed squared is the D pressure, D energy density. So constraining the derivative is tougher than constraining the individual values. But we're starting to get hints, as had existed before, that it is at least very likely that in some of the density range, the sound speed is greater than 1 over the square root of 3 times C, which is an important quantity in QCD.
so that was a
Yes.
That's interesting. Like,
Thank you.
I'm trying to understand, especially for these objects that are in isolation, why do they have persistent hot spots, and how persistent, like how long do they last?
Yes, the question is, why are there persistent hot spots and how long do they last? Yeah, and that's an important question. The answer, and this is all theoretical, of course, because we see them and so they exist, but the theoretical expectation beforehand and the observation of the X-ray hotspots is interpreted by realizing that these are radio emitting rotating neutron stars. So the radio emission requires that you have the generation of pair cascades that bounce back and forth at high Lorentz factor around the magnetic fields. Lorentz factors might typically be 10 to the 7. So the electrons and positrons that are produced in these pair cascades then slam into the surface and deposit energy. That is how we believe they happen. One other thing, by the way, to follow up your question in terms of the persistence, something we certainly have worried about is how do we know that over the years of observation that we're doing, that the locations, the nature of the spots is actually the same throughout. And a test we have done, which at least indicates there's at a crude level not much of a change, is we can actually just divide the data into halves or thirds and directly compare. And the answer is it's fully consistent with being a stable structure.
So I think on the previous slide from this one, so the one we have a different question, please. So the melting process and the polytrope envelope seem to have roughly the same shape, whereas the spectral one is more bulgy and wider. Is there a quick explanation for why that would be the case? Or is it simply just that they're different things, but they see different shapes?
So the question is kind of looking at the shape of the spectral equation state versus the others, that there appear to be interesting differences between the spectral and the other two. I don't know if there's a simple answer. One thing that may or may not be relevant is that using the priors on the parameters of the spectral model, this excludes from the outset any strong first order phase transitions, whereas the piecewise polytrope and the Gaussian processes allow that. Whether that explains what you're seeing, I don't know for sure, but that is a difference.
Jonas.
So NASA radios are of course very important for us and interesting, but also for an astrophysicist, the rest of the parameters are also quite carry some kind of predictive power. So for example, how well can you constrain the spot size or location, or for example, the break of the antipodality and all of these pulsar parameters basically?
Right, exactly. So let's see, is this the one?
Repeat the question.
Yeah, first of all, I have to make sure that I might as well just send through here. So I have lots and lots of backup slides, as you can tell. Let's see here. So this, this is going to be a little movie. So the question was, how well can we constrain other aspects of the model? Because the mass and radius are kind of the headline things, but can we talk about the spot size, the spot location? Can we rule out that the spots are antipodal from each other? So here's a movie where you have one spot and then another, and these are small spots, and you can tell these are not antipodal to each other. So it depends on exactly what you want to constrain. This, to high confidence, is not an antipodal spot distribution, meaning that if you draw a line between the centers of the two spots, they do not go through the center of the star. This is not that surprising, actually. When you look at cases where we actually can measure things with high precision, say Uranus or Neptune, they're not center dipoles. And the other pulsar, the solitary one, is even farther away from this, but it's not that far away either. So this is kind of a couple of small spots. As far as the shape of the spot, we really can't say. Here are circles, we've tried ovals, it doesn't make any difference. Remember, this has a low X-ray flux, so there's a limit to how much we can get out of it.
Okay, I think this is it. Thank you very much, Cole. This is probably a good time to thank Cole once again.
Thank you.
Remind you, people here come out for a glass of wine or cheese, and those who are watching on by Zoom, have a glass of virtual wine with us, please.
Thank you, everyone.
Thank you. It's Dick Manchester here, Cole. Just before we broke up, I just wanted to say I really enjoyed your talk. Great talk. It's nice to see some old friends again, including both of you.
Thank you. I appreciate that.
It's been a long time. I had one or a couple of comments really. One is a small correction.
Oh, sorry.
Joe Taylor and Russell Holst got the Nobel Prize for discovering the double pulsar system. If it had been for the GR tests, it would have been Joe Taylor and Joel Weisberg.
Yeah.
Joe always credits Joel with a lot of the work for the GR thing.
Yeah, good.
The other comment I wanted to make was you mentioned sort of obliquely the double pulsar results. Yeah. We've just submitted a paper giving 16 years of timing data on the double pulsar, and Michael Kramer is the lead author, and so that's has big improvements in all these tests, including many new previously unseen phenomena.
In fact, Dick, since you're on, I've not been able to get from people. I know there was initially very high optimism that within a few years of the initial 2003 report, that the moment of inertia could be obtained to within 10% based on extra precession. Is there a simple reason why it has been so much more challenging than that?
Probably not a simple reason. I think there are some other effects, as I mentioned, that higher order terms that we've had to take into account. Mm-hmm. We are homing in on it though, and the constraints on the EOS are getting tighter, but whether I don't think they've quite reached 10% yet.
Okay. Well, I mean, certainly when that happens, it's going to be fantastic.
We're getting close to that, actually.
Is it likely, like within the next 5 or 10 years?
It's very hard to predict.
Sure.
I think that time frame is probably realistic. Yeah.
Oh, that'll be wonderful. That'll be a big addition to our understanding. Great.
Anyway, great to see you again.
Wonderful to see you too. Hey, Dieter.
Hey, Cole. Good to see you indeed. Thank you for a wonderful talk. I'm so glad you could deliver it in person in Aspen, in lovely, beautiful Aspen. I have just a very quick question related to either the current data or maybe in the near future. Is there enough diagnostic power to say something about or verify the idea of nuclear pulsar?
You know, we were actually talking about that at lunch. And I think, well, Gordon's view is that the effect of nuclear pulsar would likely be on the cooling of neutron stars. It's unlikely to have much of an influence on the kind of bulk measurables like the mass, radius, or tidal deformability that we're talking about here. So we'd need to be able to get to a state where we can measure the temperature, the age, and the mass quite reliably, and then you start breaking some compositional degeneracies.
Oh, that's too bad, but it is what it is.
Hey,
Thanks again. Good seeing you all.
Good to see you. Hey, Sanjay.
Hi, Cole. Thanks for an excellent talk. I'm sorry not to be there with you to enjoy it in person, but it was great to view this on Zoom. I just had a minor comment about a question that you received about the speed of sound. And we should discuss this more when I'm in Aspen in 2 weeks' time. But the key is, if you believe nuclear physics at low density, and I think there's good reason to do that, below twice nuclear density, and hopefully experiments will improve our understanding at these lower densities in the coming years. And you have a 2 solar mass neutron star that has a radius that is greater than about 12.5 kilometers. Then you are going to be forced to have a speed of sound that is very large. And by very large, I mean close to the speed of light. And that is remarkable. I mean, if we can just combine low density physics from nuclear experiments in nuclear theory and a 2 solar mass observation, which I think is also very special because it probes these high densities, knowing that the radius is greater than 12.5 kilometers will be very important. So your range that goes out almost to 16 kilometers, most of that range will be strongly in favor of extreme speeds of sound.
Okay. Fantastic. Yeah. So you're going to be here not next week, but the week after, right, Sanjay?
On the 10th of July, yes.
Okay. Well, one of the things I just wanted to mention is that, of course, we have various discussions like the 2 per week. And I think the current plan is that not next week, but the following week when you'll be here is when I am going to pin myself against a blackboard and try to dodge arrows from everybody as they ask detailed questions about what we're doing. So
okay, that's great. Do you know in advance when that will be?
I don't think we've decided quite yet. Yeah, we have Wednesday and Thursday sessions is the current weekly schedule.
Tuesday or Thursday.
Tuesday or Thursday? Should
Yeah, normally we want Tuesday. Thursday.
Oh, I see. Okay, so apparently it's either Tuesday or Thursday of that week.
I better go get my arrows then.
I'll get my suit of armor.
Okay. All right. Nice talk. Thanks very much.
Hi, Sanjay.
Thank you.
Hi, Gordon.
See you see you in 10 days. Great.
Yeah, looking forward to it.
Good.
All right. Bye, everyone.
Bye.